Right, so I'm going to start with a mihi, and then we're going to get into the presentation. Tēnā koutou katoa, ko matarangi te monga, ko te whanganuiatara te moana, no te upoko o te ika a Maui a ho, ko Ford toku whānau, ko James toku ingoa, tēnā tātou katoa. Welcome to my talk on creating 3D printed landscape models with FOSS. I have one here as a little prop. Thank you, Linz. I'll quickly introduce myself and what I plan on covering today, and then we'll dive into it. Quick note, so the first part of this presentation is going to be via slides, and the second part is going to be a couple of live demos. And just with the screen sharing, there'll be a bit of me jumping to the side, and I apologize for any disruptions that happen as a result of this. So, who am I? My name's James. I'm a senior GIS analyst at Wellington City Council. I'm also a freelance cartographer under the name Obsidian Cartography, hence the name of the talk and the branding on the slides. I've got a focus on terrain, mountains, and volcanism, and I use a FOSS stack, primarily QGIS, Python, Blender, and I'm now counting Affinity because it's free even though it's not open source. And today's talk is on demystifying 3D printing. So naturally, as someone who's into GIS, a bit of a GIS nerd, and with disposable income, I reached the point where I decided I'm going to buy myself a 3D printer because they're accessible and it looks like fun. What's better than having a mountain on your screen? Having one you can physically hold. And then I dived into how do I get from having a raster to having a physical 3D model that I can hold? And I went through the stages of figuring out the simple answer and then getting lost in a rabbit hole and coming up with a complicated solution which makes life really easy and has quite a bit behind it using Blender, and that's the bit I'm quite excited to show you at the end. So, first part will be on going from raster to having a physical 3D print. Then it'll be how do you make a digital 3D model with QGIS, the easy way. A bit on validating your digital 3D models in Blender. Then how you take a digital 3D model with a slicing program and turn it into G code, which you can then use in a 3D printer to make a model. And then the final part is that cool Blender setup, which I'm going to show you at the end. So before we 3D print something, we need to pick an area to 3D print. And since we're in Tamaki Makaurau, Auckland, Rangitoto Island out in the harbour, I think is a very fitting location, which this 3D model is of. It's a shield volcano, which is quite large and flat, and that makes it a bit of a challenge to make a suitable 3D model from. So how do you go from a raster to a 3D print? You start with a raster, and then you have to turn it into a 3D mesh, and then you slice that 3D mesh into G-code, and then you can print. You can actually skip some of those steps, so you don't even have to make your own 3D mesh. You can just buy one online, though making it yourself with QGIS is pretty easy. And then when you've got your 3D mesh, you don't have to slice into G-code and have a printer. You can use an online printing service. So it is actually really easy to get into this stuff, but I think it's more interesting if you understand how the whole process works. So there are two plugins currently available in QGIS for 3D printing. One is the STL generator plugin, and the other is the, I can't read that, DEM to 3D. I don't know the names of these because I have my own setup, but this is for your benefit. So the still generator plugin is super easy. You just need an input raster with all the no data values filled, specifies the size you want, press go, and it makes one for you. And then that's super easy. The DEM to 3D printing plugin gives you more options and a bit more flexibility, but essentially does the same things. You figure out what settings you want, you fill them out, you press go, and then you get a model you can use. So once you've got your model, that doesn't necessarily mean that you can just go ahead and print it. It has to be a valid 3D mesh, and this is where Blender can come in useful. So there's a plugin in Blender called 3D Print Toolbox, and that has a tool that allows you to validate and fix your mesh specifically for manifold issues, which is probably what will cause your print to fail if those are present. So that is super easy to install, and then you can just load in that still file, that 3D mesh you generated in QGIS, clean it, export it, and then you're ready to go. So this is what our 3D mesh looks like after we create it in QGIS. But if we look at the side, it's super flat, and that's a little bit of a problem because then you end up with a 3D print which you can't really see anything. So this is a problem with scale. You could reduce the extent of your 3D print, the geographic extent, and focus right on the cone of the volcano, and then you'd actually have some elevation showing because the z-axis scales with the horizontal axis. But if you're using these plugins in QGIS, it means each time you have to go back through that process of picking your extent, putting in your settings, exporting it, and then checking the result in Blender, which isn't hard. It's just a little bit time consuming, and you can't see the changes as you're putting in the settings, which is why I tried to solve that with Blender. So before I show you the Blender setup, I'm going to show you how a slicing program works and tell you a bit about what the difference is between a 3D mesh and G-code. Sorry, bear with me. Here we go. So this is Cura Slicer. It is free and open source. You don't need a 3D printer to use this, but you do need to pick a 3D printer model and the nozzle size and the type of filament that you plan on using. That's because that helps inform the G-code, which is produced by the program. So what G-code is, so I think it counts as like a programming language. It's a programming language for 3D printers and CNC routers, and it's a set of directions which tells your 3D printer or CNC router where to move the printing head or the routing bit, how fast to move it, and then in case of this 3D printer, what temperature the nozzle should be and how fast it should be pushing out plastic to make your 3D model. And those variables will change based on what 3D print you have and what filament you're using. We won't go into those, but that's for context. So your slicing program takes your 3D model, which you can just drag and drop. In this case, I've used the slicing program to reorient my 3D model. So instead of having it flat, I've got it vertical. And the reason for that is that you've got variable resolution in printing. So the resolution on the X and Y axis is the width of your printer nozzle, which tends to be 400 microns, so 0.4 of a millimeter, which you think is really detailed, and to an extent it is. But then on the Z-axis, you can get as detailed as 50 microns with some models, which shows far more detail. And so you have one axis in the vertical direction, which is really detailed, and then your two other axes, which is less detailed. And what happens is when you print it, you end up with kind of like contour lines, and it looks like a stack of pancakes when you print it out. And this can look great, and that's what's done with this model here, if you want to come up and have a quick look at it after this talk. But a little hack you can do is by switching the orientation of your model, you're then making it so either the X or Y axis is now that high resolution. And so it means when you're looking in one direction on the printed 3D model, it looks like it's got 50 micron resolution instead of 400, and that gives a much better result. And even though it's only in one direction, you don't have that pancake contour look, and you get much better results. So slicing program, you can import your model, and then just rotate it. Super easy. Put it 90 degrees and you're done. So you've got a model, it's passed all its checks, it's valid because we did the cleanup in Blender. Then there's a bunch of settings you can choose. So one of them is layer height, and that's the resolution in that z-axis dimension. And then you've got some key settings around strength. So how a 3D model, a 3D printed model isn't solid plastic. It's usually got a semi-hollow interior, which is what we call infill. And there's different design patterns you can have that give strength for that, and you can have different infill percentages. So if you use a commercial 3D printing service, usually they'll just do a standard 15% infill, which will give you a strong 3D model, and it's great. But the more infill and material you have, the longer it will take to print, and the more material you're using, so the more expensive it is. And if you're doing this at home, you might want to save time and money, because you're not building a functional tool or object. You just want to have a 3D printed landscape to put on the wall somewhere. You're not going to be like trying to bend or break it, so strength isn't super important. And what you can do is you can increase the outer wall layers, the number of layers for the exterior of the model, the shell, and that increases a lot of strength. And then you can reduce that infill to, I find you can reduce it to about 5% without having anything catastrophic happening. And then since we've rotated our model 90 degrees, we might have some mountains sticking out with nothing beneath them to support it when the plastic's printed up. And so we might need to generate some supports, and that's what you can do in the slicing program as well. And those are auto-generated for you. And then when you're ready, you can press slice and you get the results. And so this is really handy. It's converted your model into G-code, which you can then send to a printer and print. But it also gives you a breakdown of how much material you're using, how long it's going to take to print, where the material is being put. Is it all in the infill, or is it all in the exterior shell, or is a lot going to supports? And you can see down the bottom, that blue area, this is where some supports have been generated just to keep the model stable while it's printing. And if we look at it from above, we can see we have our gyroid fill. So we're printing faster and we're saving material because we've done some customization, and all with a piece of FOSS software. So if this is something that interests you, I encourage you to download it and have a play. You don't necessarily have to use Cura Slicer. There's like a dozen different slicing programs. Usually what all the 3D printing companies will do is they will take Orca or Cura, which is another FOSS slicer, and then they will just make their own version based off that, which has basically all the same functionality, but I guess it might be a little bit nicer to use if you have the same model printer, which is what I do. But FOSS4G, so I'm presenting on the FOSS option. Right, so we'll sneak back to the slides. Right, so final part of the presentation, which we can dedicate the most time to, is how do we level up a game when it comes to 3D model creation, going from that raster to 3D model. And the tool of choice for me is Blender. Admittedly, I don't know any other FOSS 3D modeling tools, so it's my only choice. But I think I've come up with something that might be quite useful to people. So this is it, and I'll walk you through how it all works in a moment. But the idea is that the settings are all dynamic. So I can change the size of my model to 25 centimeters by 10 centimeters and have that update live. I can actually view the raw mesh instead of just the surface. And if I want, I can change the resolution. So I can make it look real simple. Or I can make it crazy detailed. And so you don't necessarily need a super detailed model for 3D printing, but generally you want a detailed enough model that you can make use of the native resolution of your 3D printer. But if you're just trying to explore the model in 3D and regenerate it dynamically, it makes sense to have a lower resolution model, because then you won't be pushing your computer to the limit. And certainly my laptop can't handle too much, so we're going to simplify this back down. So another cool thing this does is that, sorry, I'm working off two different computers on a tiny screen, so it takes a moment to get my bearings. So what I quite like about this is I've set it up so you can do dynamic transformations between the model space and the raster space. So this uses quite a large extent for a DEM, which I prepared in QGIS. But I've made some tweaks with how the transform between the raster image and the model, how it tells the model where to displace the height values, so that we can actually shift that relationship. So we can zoom in and out, we can rotate it if we want. There we go. And we can also do some horizontal translations in map units, which is super handy. So we can change the center of what shows up in our model. And if we decide to zoom all the way out, it doesn't break everything, which is a nice feature. So how does this actually work? I'll have to rush through this, I think. So Blender is 3D modeling software. It allows you to either generate things manually or procedurally generate things. If we were to do this the manual way, we would go and create a mesh grid. And that gives us settings like what size we want, how many subdivisions, and what is the location going to be. And when that's made, that's fixed. You can't go back and change it. I mean, you can scale the size, you can change the position, but you can't change the subdivisions, which means this is no longer dynamic, and you've got a similar problem to QGIS where you have to go back to the beginning if you want to change that setting, which is the subdivisions. But instead, we can use something called geometry nodes, which is the tool for procedural geometry generation. There we go. So if we switch over to this tab, we can see we've got a node-based workflow tool, which allows us to define some inputs, which then appears for us to use on the right-hand side and change. And we can see how those inputs are used. So we can take the number of subdivisions, add 2 to it, so we get the corners of the mesh, and that goes for the input to the creation, and then we've got the X and Y size. And that's the super simple example of geometry nodes, and it is super handy. And then the complicated version looks something like this. Which is a bit of a mess. And the reason for this is because we have to do all the UV transforms. And I realize I'm running out of time, but how this works is we create our mesh surface. We also have to create a base for it, which means generating mesh faces for the sides and the base. For all those vertices which we have on that top surface, which is our terrain, we make it look like terrain by displacing them with a vertical offset. And to do that, we need to know the scale of the real world data to the model data, and we need to correct the aspect ratio of the raster that you're using and the shape of the mesh. So if you have a rectangular raster, you're going to have to apply that aspect ratio of the long side to the short side to the UV transformation. A UV transformation is, it takes one corner of the raster and puts it on one corner of the mesh, and then does that for all 4 corners. So if you have a square raster and a square mesh, it works perfectly. But if one or both of those are rectangular, then your data gets squished and pulled in different directions, and it doesn't work. It's not correct. So you need to correct for those aspect ratios, and then use the real world size and the model side to figure out your scale. And yeah. Sorry, I've got a bit lost having to switch between these computers. But the general idea is, if you know how to use Blender and you know how to use geometry nodes and you understand the math, you can create a process like this, which allows you to dynamically create 3D models for 3D printing. And I would love to share this with all of you, but as you can see by these geometry nodes, it's not exactly clean. And I feel like having a write-up for this, both on how this works and how you can install and use this yourself, is essential. So bear with me. I will put that together and you can enjoy it. And if you want to just get your hands on this project, just flick me an email or come and talk to me afterwards, and I'll just give it to you. With a disclaimer that it is as is. So yeah, thank you for attending my talk, and absolutely flawless live demonstration. If you want to keep in touch, here's some QR codes. So my website is currently being rebuilt, so LinkedIn or email is the best way to contact me. You first?
I've done one of those prints, and it was good, and it looked like the pancakes you mentioned. So
yeah.
But I was wondering whether you have been faced with a situation. I've seen on the island, in the VM, you can see some finer structure, like let's say the path around the caldera. It seems like there is a broken path or something. Have you tried to somehow emphasize, if you don't want to lose those with the exaggerations that like, if you want to show detail of the line.
If you want to show the detail, you either have to make a really big model, or you have to zoom all the way in and it cut a whole lot of stuff out. There's not really any.
I'm wondering if there's an equivalent to cartographic generalization techniques applied to 3D models.
If you have 3D modeling skills, 100%, you can just go ahead and edit the model and flatten bits out manually. You can definitely do it, but and you could certainly update a geometry node setup to do that for you automatically, but that's not something I've tried. So yes, it's possible. I can't help you any more than that.
Okay. Oh, I had a question nearly along the same lines as him. So I think physical relief maps have been around for quite a long time, and from what I gather, they often emphasize topology by exaggerating the z-axis. Or I suppose this is more of a comment, but I suppose would that be quite easy to do?
Yeah, it is.
I mean, just by adding a multiplier to the z-axis.
Yeah, I have actually done that. I just didn't get around to demonstrating it. So if we have a look in here. Where is it? Vertical exaggeration. Yeah, yeah. Obviously, you don't want to exaggerate something that much, but yes, you literally just add in a multiplier.
Yeah, okay.
Oh.
So I get it's dynamic and you can customize it a lot more, but are there any real advantages to doing it in Blender over just like the 3D and QGIS? Because that does offer.
It's literally just whatever's easiest for you. For you, it sounds like using it in QGIS is fine and much easier. For me, I'm in the process of developing a 3D printed product, and I wanted to be able to sub in and out different DEMs and zoom in and scale and rotate them. And making the setup, despite it taking like days of figuring out and banging my head against the wall, has saved me an awful lot of time. So for me, yes, it's better doing it this way. For you, probably not. To each their own.
And one more question. So some of the cooler terrain features are hard to capture in DEMs, like archways and tunnels, you know, with a lot of islands. Like archways and stuff like that. Have you had any thought about how it would be possible to 3D print something like that?
Well, you wouldn't use a DEM for that because DEM is 2.5D. If you've got LiDAR, then you would triangulate it, and then you'd likely need to do some editing of the 3D mesh you'd created. I haven't tried doing that in Blender, but I'm sure it's possible. Whether it's the right tool, I don't know. If you do any of that, flick me an email because that sounds super cool. Do we have time for any more questions? No. Any questions, just find me and talk to me during the conference. Thank you for attending my talk. I hope you enjoyed it.